The feasibility of the um, full model approach to calculating power depends critically on being able to solve two equations in an efficient way. One of them is this nonlinear equation, which talks about a future output voltage equaling V min based on some constant input current, and the other is this output equation equaling V max based on some different input current criteria. We need an efficient way to solve for a root of a nonlinear equation. And there's a number of ways of doing so. The bisection search algorithm is one quite good way to do so. A bisection algorithm looks for a root of some function, h of x. So by root we mean a location x such that h of x is 0. Where we know beforehand that there's at least one root between x1 and x2. So we supply the algorithm with limits x1 and x2, and we know that there's a root in between, and we want to find that root. One way of knowing that there's a root in that interval is that the sign of h1 is different from the sign of h2. And that's kind of key for how this algorithm ends up getting implemented. Now, if the signs are different, it's possible that there are two roots in between in general, and the bisection method is guaranteed to find one of those only. In our case, just by the nature of the problem, there will only be one root, and so we'll be okay. The picture on the right shows the kind of generic idea where h of x is some nonlinear function, and you can see that it passes through 0, be somewhere between x1 and x2. And what we do is we start out with knowledge of the sign of the function at x1 and the sign of the function at x2, and we compute the midpoint halfway between x1 and x2, that's x mid, and we evaluate the sign of the function there. And then we replace either x1 or x2 with that midpoint. And we do that in such a way that we maintain the sign difference between x1 and x2. So in this case, we are going to eliminate x2 and replace x2 with x mid. And then we repeat. We compute a new x mid, which is somewhere around here. And we evaluate the function there, and we say, oh, it's negative. So to maintain the sign of x1 and x2 being different, I now replace the x1 with that point. And then we do it again. Here's my new x mid. So I replace x2 with that point. Every iteration that we perform cuts the region between x1 and x2 in half. So we are reducing the uncertainty of where the root lies by a factor of 2 every iteration. And we repeat this until we have isolated the root to within enough accuracy for our final objective. So the resolution then is of the root is as small as desired. And we can pre-compute the desired number, or the number of iterations that are required to do this. So suppose epsilon is the desired root resolution, then the algorithm requires at most, this is the ceiling operator that rounds up to the next highest integer, log base 2 of the absolute difference between x2 and x1, all divided by epsilon. That's saying that we start out with an uncertainty between x2 and x1. We want that uncertainty to be epsilon, so it's that many factors of epsilon to begin with, and the log base 2 reflects the fact that we cut the uncertainty in half every iteration, and we'll get some decimal number, so we have to round that up to get the integer number of iterations required. The algorithm can be implemented in MATLAB quite easily, and here's an example of doing so. This is just a generic bisection algorithm where x is the output location of the root, bisect is the name we'll call it, h is the function that I am trying to find the root in in which I'm trying to find the root. X1 and X2 are the bracket points where they straddle somehow this root location, and TOL is the tolerance or the epsilon value in the previous equation that says the desired resolution. I want to be closer to the root than tall. We start out by pre-computing the number of iterations at most that we will have to do of the bisection algorithm. We say it's the ceiling of the log base 2 of the absolute value of x2 minus x1 all divided by tolerance. A simple implementation of that previous equation. Then we set up, we say dx is the distance between x2 and x1, and we are organizing x1 and x2 such that we want h of x1 to be negative and h of x2 to be positive. So if it turns out that h of x1 is positive, then I'm looking in the other direction and I set x1 equal to x2. Otherwise, I just leave everything alone. And by the time I get to this point, we have that the root is between x1 and x1 plus dx, where dx may be a negative number, and h of x1 is the negative value, and h of x2, or h of x1 plus dx, is the positive value. Now I go through a bunch of iterations up to j max, where this is j max. I do that many at most. I say this is my new dx halfway through, and x mid is x1 plus dx. And I say, is h of x mid less than or equal to 0? If so, remember h of x1 I want to be negative. So if the middle point is negative, then I replace x1 with the middle point. Otherwise, I am really just replacing x2 with the x mid, but I've already done that in essence by saying dx is a half times dx, so I don't have to worry about updating an x2. I just have already updated dx to compensate. And if absolute value of dx, this interval, is less than the tolerance, then I stop. I stop the for loop. Otherwise, I keep on looping the j max times, and I return to the calling procedure x1 plus 0.5 times dx. That is my best guess. I know that the root is between x1 and x1 plus dx. I know that that is true, but my best estimate then is the midpoint, which means if I returned x1, I could be off by a full dx. If I returned x1 plus dx, I could be off by a full dx. But by returning the midpoint, I'm off at most by dx over 2. And so I get a nice accurate estimate of where that root location is. So there we go. There's a procedure to perform bisection. Here's an example of how to use the procedure on something we know about to begin with, and it's the function x cubed. X cubed looks like this. We know the root is at 0, but I am creating a new inline function here, h equals at x, that says this is an inline function where the variable is x, and the function is x cubed. And then I bisect using that function handle between -1 and +2, so between there and there, and my tolerance is 10 to the -5. And what it returns to me, it doesn't return 0, which is the exact location of the root. It returns about -1 times 10 to the -6, which is pretty close to 0. In fact, it's closer to 0 than my tolerance, so this has, in fact, succeeded quite well in finding that. So that's a simple example of how to use the bisect function, but we need to be able to use it with a cell model, so we need to figure out how to do that. So overall, we are going to do 3 simulations delta t seconds in the future, k delta t samples in the future, same thing. We are going to simulate this cell for 0 current, for the Imin current, where that is the design limit Imin and Imax current. And if the cell voltages are predicted to be within the bounds for the maximum rates, then we can use the maximum rates and not have to bisect at all. We have completely avoided bisecting because the cell can handle the maximum current. If the cell voltages even during rest are outside of bounds, then we have an error situation. The cell is already outside of the proper operating limits, and that's bad. So we set the maximum rates to 0 and inform the vehicle or the load that something went wrong. Otherwise, if I use Imax or Imin, the voltages are outside of bounds, but I use I equal to 0 and they're inside of bounds, I've got some bisection limits. I can bisect for between Imin at 0 for charging and 0 and Imax for discharging in order to figure out what current is available from this battery cell for the next k delta t samples. So we need then to create a bisection function h, if you will, that I can use with the bisection code that simulates the ESC model for k delta t samples in order to see what value of current is going to give me the right limits. The ESC model state equation is linear for a constant current, and to be able to use that, I'm going to define matrix functions A and B. A is not, in fact, a constant matrix, but it is constant if current is constant, and the same with B. So notice A here is my A matrix, but it's a function. It's a function of IK, which is current. It's a diagonal matrix. I've got the state of charge state up top. I've got the diffusion resistor current state in the middle, and then I have the hysteresis state on the bottom, and the hysteresis state update value is a function of IK. So for a specific value of IK, the A matrix is constant, but for different IK, I have different A matrices. So that's why I write A as a function of IK. I write B as a function of IK also. And again, we see the functionality, the functional dependence rather, in the hysteresis input term. So I have A matrices and B matrices now for a specific value of current. And for that current constant over the prediction horizon, remember we said this, that the future state is equal to the present state pre-multiplied by the A matrix to the k delta t power plus this term times the input un. The A matrix in our case is diagonal. Look at it. It's diagonal there. So the matrix exponential is simply the diagonal matrix comprising the scalar exponential of the diagonal elements. So that's easy. Maybe I should say power, matrix power, because matrix exponential does have a slightly different meaning technically. So this here, the left term is easy, but this term on the right needs some closer inspection. So the summation, so B is constant, that does not need to be in the summation, but the summation of the other term here, for j equals 0 to k delta t minus 1 of A to the k delta t minus 1 minus j power, I can take that and write it as A to the k delta t minus 1 times A to the minus j. I can factor that out. This is not a function of j, so it comes outside of the summation. And so inside the summation, I go from j equals 0 to k delta t minus 1 of A to the minus j power. Now I can use the geometric summation formula specialized to a matrix case in order to compute this. And this notation here is not quite right because I can't divide matrices. So by the time you get these notes, I will have fixed it. But this needs to be times inverse of that instead of divided by. So it's either pre-multiplied or post-multiplied by the inverse. I will fix that by the time you see it in your notes, but that's the general idea. If I'm dealing with scalars, of course, it works without worrying about order of operations of matrices. And if I'm realizing that the A matrix is diagonal and the identity matrix is diagonal also, that if I do the elements one at a time, I also can do the division instead of worrying about multiplying by inverse matrices. In any case, let's pretend this is right, even though it's not quite right. And we notice then that the geometric sum of a finite sum would normally be 1 minus a to the limit plus 1, which is what I have there. And I have the minus there, becomes the minus there too. And then 1 minus a to the 1 power, but with the minus because of that minus j. I multiply the numerator through on the left by this, which gives me the numerator that you see, and then I multiply the top and the bottom of this by a, which gives the simplified form here. And again, I'm going to have to carefully check the matrix algebra to figure out if I pre-multiply by the inverse or post-multiply by the inverse to make that true. But this summation started out looking kind of messy, but it ends up with a deterministic equation, which is not so messy. It's actually quite easy to evaluate, and it allows us to write quite efficient code. So I have code here, simcell kdt for k delta t seconds in the future, which returns the voltage and the state, delta t seconds, or delta t samples rather, into the future. And I have a constant current input, I have an initial state, I've got the A and B matrix functions, I've got the number of samples, temperature, the model, and then some model parameters, which could be useful. The A matrix, this A is a function of ik, and for a specific value of ik, I evaluate that function and get a matrix back. So A matrix is a constant matrix, so is the B matrix here. It's the B function evaluated at ik. And then dA is the diagonal elements, comprises the diagonal elements of the A matrix. So dA is a vector. There is a special case of the equation. If you go through and you find out what the A matrix is when current equals 0, if we use the summation formula that we have, the finite geometric sum, it turns out that we have a problem. We have a divide by 0 because the formula doesn't actually work in that case. So we brute force calculate what happens when current equals 0 and we get this. So the integrator state, we just add up kdt samples of current to add to the SOC variable. The diffusion resistor value, we use that formula from the previous page, and then for the hysteresis state, we just add up the hysteresis. In fact, it stays the same. And then similarly, when we don't have 0 current, we can use that formula on the diffusion resistor currents and on the hysteresis state, both. So ADT is that summation at the bottom of the previous page, and we update the X state as the diagonal elements of A to the kdt power multiplying the initial state, or the present state value x0, plus this ADT summation multiplying the B matrix, multiplying the input over this fixed period of time. And so that's the future state. The future voltage is OCV minus diffusion voltages plus hysteresis voltages minus the IR terms. So this works if I'm charging or discharging, doesn't matter. It simulates the cell. the kdt samples into the future with a constant current of Ik. Now I can use that as the basis for writing a cost function for the bisection algorithm. So if I'm bisecting on discharge, I will get the voltage and the state from simulating the cell with a discharge current, but then my bisection function is based on whether the voltage exceeds a voltage or the state of charge exceeds a state of charge. So I need to make sure that the maximum of min volt minus the predicted voltage and Zmax minus the state of charge state must be less than 0. And that will then enforce both limits if I use that as my output. And see, I have a typo here. That should be H in both places. And the same for charging. I want to make sure that the maximum voltage is not exceeded and the maximum SOC is not exceeded there. There may be some corrections to this before you get it. I see a couple things I want to look at, but the general idea is to try to make the bisection not look only at voltage or only at state of charge, but look at both of them while we're doing this. And then to use one of these functions, we use code like this, and we say H is my bisection function on discharge, and then I say the current limit is just bisecting between I min and I max with some I tolerance, and we can compute the values. So that's the general idea. You'll have a homework project that's based on this. So hopefully I get most of the errors out of the notes before you work on the project, and then you can find the rest of them and tell me where they were. And then we'll get to see how this works in practice.